Okay, folks, so we're going to be talking about this. We're going to be talking about bond and molecule polarity. But before we even talk about this, we need to talk about something else. Okay, we need to talk about, what should we talk about? Let's talk about electronegativity. Okay, we have spoken about this before. Okay, so we have spoken about this before. But just to recap, then will help us to understand this better. Electronegativity is the ability to pull electrons towards one's own nucleus, okay, while being bonded in a covalent bond. Okay, so basically what does this mean? It basically means that all atoms, okay, it basically means that all atoms when they are attached to another atom in a covalent bond, they end up attracting electrons towards themselves. For example, okay, let's say we have A and we have B. Let's say this is the electron of A and this is the electron of B. They are supposed to be sharing these electrons, right? They're supposed to be sharing these electrons. So let's put B over here. So you notice there are two boxes between A and the electrons, and there are two boxes between B and the electron, right? You see, since A is not the same as B, okay, they're not the same, that means they're different. What will happen is these electrons which are shared will be closer towards one of the atoms, okay, will be closer. So it's supposed to be here, right in the middle, but instead of that, it could be a bit closer to B, could be, all right? It becomes closer to B. So when this happens, what we say is, we say B is more electronegative than A. That's what we say, okay? So when we represent this as a bond, we normally draw it like this, A, and then we B, and then we draw a bond, and we put an arrow. So the arrow basically means that the electrons are being pulled by B. And when this happens, what we usually do is we put a small sign here, positive, and a small sign here, negative. Okay, this is actually delta. Okay, delta. This symbol basically means small. Okay, so it basically means a small positive charge and a small negative charge. Small. So it's a very small charge that is happening here. Okay, so B is more electronegative than A. So this bond, we say this bond is polar. Okay, this bond is polar. So the bond is polar. And then we say AB, the molecule AB, is polar. So this is a polar molecule. Okay, this is a polar molecule. All right, so this is a very important concept here. The atom that pulls electron more towards itself is more electronegative. The bond that exists between the two atoms is polar, and the entire molecule becomes polar. For example, okay, let's say HCl. Now in HCl, H is less electronegative than chlorine. So there is a table that you can check out. So like, for example, in this table, hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. Okay, there's a table. You don't have to memorize this table. So chlorine has an electronegativity of 3.0. Hydrogen is 2.1. So you can see that chlorine is more electronegative than hydrogen. So what will happen is chlorine is slightly negative and this is slightly positive. So this bond is polar. The bond is polar, and we say HCl is a polar molecule. Okay, HCl is a polar molecule. So to make things a little bit easier, you don't need some memorization going on here. If in this periodic table, what is happening is this way, electronegativity is increasing, and this way, electronegativity is decreasing. Okay, so as we are going that side, electronegativity is increasing. So in the periodic table, or in our universe or our world at the moment, the most electronegativity is fluorine, then followed by oxygen, then nitrogen 3.0, and closely followed by chlorine, which is also 3.0. So these are the most electronegative. So the three most electronegative is this. These are the three most. And then if you wonder why nitrogen versus chlorine both also have the same value, but why is it different, is simply because chlorine is bigger. Okay, chlorine is bigger compared to nitrogen. Nitrogen is a little bit smaller because it's only made up of 2 shells. So that is why third place goes to nitrogen, because it's smaller, it's able to attract things much more closer to itself. So basically, as the electronegativity changes, then the polarity also will change. That means if there are less electronegativity, negative, the polarity also becomes less. Okay, but as far as you are concerned, if there are 2 different atoms, the bond is polar. Okay, the bond is polar. So now we're going to be looking at things which are a little bit more complicated. Okay, a little bit more complicated. Like for example, we want to look at molecules which are made up of more than one atom. Okay, more than one atom. So for example, let's say, like for example, let's take methane. Okay, let's take methane. Let's start off with methane. Methane is tetrahedral, right? Methane is tetrahedral. When I say they're tetrahedral, basically all angles in between the hydrogens and the carbon, that means the angle here, this angle is 109.5. Okay, so every single angle is the same. Every single angle is the same. So we say methane is symmetrical. Okay, we say methane is symmetrical because all angles are the same. Okay, all angles are the same, so which means that means the molecule is symmetrical. Okay, second thing I want you to notice is all peripheral atoms are identical. You see, notice all the peripheral atoms, they're all identical. They're all the same. Okay, so first of all, methane is symmetrical because all angles are the same and all peripheral atoms are symmetrical or identical. So when we look at carbon, and when we look at carbon and hydrogen, carbon's electronegativity is about 2.5. Hydrogen's electronegativity is about 2.1. You don't have to memorize this. But so there is a difference. So carbon is a little bit more electronegative than hydrogen. So the bond is polar. So this bond is polar. This bond is also polar. This bond is also polar. This bond is also polar. Every bond is polar. So the arrow is pointing towards carbon because carbon is more electronegative. Every bond is polar. Okay, so every bond is polar, but, okay, there's a big but here, but polarity of all bonds cancel out each other. Okay, the polarity of all bonds cancel, I think I spelled cancel wrongly, right? Polarities of all bonds cancel C-A-N-C-E-L, cancel, okay, out each other. Polarity of all bonds cancel out each other because it's a symmetrical molecule. Okay, it's a symmetrical molecule. So why is it a symmetrical molecule? Because all angles are the same and all peripheral atoms are the same. Let's look at another example. Let me just add another one. current template. Okay, so let's look at methane, for example. Okay, so methane, earlier on we drew, okay, it has a hydrogen, 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 right? But what do we know about methane? So again, the example is the same because all the peripheral atoms are the same. So this bond angle is 107 or 107.5, depending on which book you're reading. So the angle between hydrogen, nitrogen, hydrogen. So the angle, okay, the angle between hydrogen, nitrogen, hydrogen is 107.5. But the angle that exists between the lone pair, the angle between the lone pair, so the angle between lone pair nitrogen and hydrogen is greater than 107.5. I don't know what it is. I don't think anybody knows. Somebody might know, but it's not 107.5. So in this case, although all peripheral atoms are the same, although all the molecule is polar. Okay, the molecule is polar. Why? Because it is not really symmetrical. Okay, let me explain this to you. You see, what is happening here is this bond is polar. So nitrogen is pulling the hydrogen away. Pulling the electron away. This is pulling the electron away. This is pulling the electron away. But the polarities of the bonds do not cancel each other out. The polarities of the bonds do not cancel each other out. See, in this case, the polarities of the bonds will cancel each other because the molecule is symmetrical. In this case, it does not. Okay, like for example, let me do a little bit of physics with you. Let's say, if you remember a little bit of physics, let's say you have a force which is acting in this direction and a force which is acting in this direction. Let's say this is 10 newtons and this way is 10 newtons. So the net force which is acting at this point is considered to be 0, right? Because they are acting in the opposite direction. Am I right? Do you remember this? So this is 10 newtons as well. Okay, 10 newtons. Okay. So the bond will cancel each other out. That means the net force at that point is 0 because it is symmetrical. That means this bond is exactly 180. So let's look at another example. Let's say this spot here. There's one force acting in that direction, another force acting in this direction, another force acting in this direction. Let's say the angle between all of this is 120. Okay, and let's say the force that is acting here is 10 newtons. Here is 10 newtons, and then here is 10 newtons. So the net force which is acting at this point is also 0. Because all the angles are the same. All the angles are the same. So which means that it will cancel each other out. So another example I can give you is like, let's say in this case now, okay, they're all 90 degrees to each other. So what will happen is the net force in the middle will be 0. Because every angle that you can find is identical. So the net force is 0. So in this case just now, since every angle is the same, the net force acting at carbon is 0. That means the molecule becomes non-polar. Although the individual bonds are polar. Like for example, right? If you go and touch this rope, the rope will have a force acting on it. That means it's not going to be loose. It's going to be very taut. Okay, it's going to be stretched out because there's a force acting. But overall, there is no force because it cancels out each other. But in this case of ammonia, the bonds are not the same. So it's like this, okay? It's like this, okay? Like this example here, right? Again, in this example, everything was 120. But imagine it was like this. Okay, imagine it was a force, one force acting this way, one force acting this way, one force acting this way. And let's say this angle was, 107, and this angle is also 107. So now you see it's actually not symmetrical, right? It's not symmetrical at all because the bonds are not cancelling out each other. There's a much bigger angle over here, right? There's a much bigger angle over here. So all the angles are not the same. So which means that in physics, this entire structure will move towards this side because the forces are acting in that direction. So the same concept applies for, let's say, this molecule, let's say water. Okay, water. Okay, so I will not use dots. Okay, let's say there's a lone pair here, there's another lone pair here, and then let's say this is the hydrogen, one hydrogen and another hydrogen. This angle is 104.5 degrees Celsius. Okay, so what is happening here is this angle is greater than 104.5. Meanwhile, this angle here between the lone pairs is much greater than 104.5. So which means that now you have three sets of angles: the angle between the hydrogen, oxygen, hydrogen, the angle between the hydrogen, oxygen and lone pair, and the angle between lone pair, oxygen and lone pair. All right, there are three sets of angles. So this molecule is of course not symmetrical. All right, it's not symmetrical, and since oxygen is polar, it's going to be pulling electrons towards itself. So although all bonds are, although there's no T here, are polar, although all bonds are polar, the molecule becomes although all bonds are polar, the molecule becomes polar, not non-polar, since there is no symmetry. Okay, since there is no symmetry, and because there is lone pair, there is no symmetry. Now, to make things simple, if you see one lone pair on central atom, let's say you see one lone pair, all right, so 100%, I better be careful what I'm saying, 100% you can rest assured that the molecule is polar. So once you draw the Lewis structure, you have drawn the Lewis structure, and you realize there's one lone pair on the central atom, rest assured that the molecule is going to be polar. Two lone pairs, little bit suspicious. Two lone pairs, they can be non-polar. Okay, like for example, if you try drawing this guy out, xenon tetrafluoride. In the case of xenon tetrafluoride, right, what you will notice is xenon, one fluorine is that direction, one fluorine is this direction, one fluorine is here, one fluorine is here. And then the lone pair is at the top and the lone pair is at the bottom. So what happens in this case is the angle between this is 90. The angle between this is 90, the angle between this is 90, the angle between this is 90. So every angle here is 90. And from the one lone pair to the other lone pair is 180. So in this case, although it has two lone pairs, this molecule turns out to be non-polar because it's symmetry. The polarities cancel each other out. Okay. Second thing I want you to know is if at least one peripheral atom is different, okay, at least one peripheral atom is different, then 100% the molecule is polar. Okay, so like in the example just now, let me just add one more page here. In the example just now, okay, in the case of methane, right? So methane was like this, correct? We have this, we have this, we have this, we have this. So I told you methane is non-polar, all right? It's non-polar. But if I remove this hydrogen, and I put, let's say anything else, let's say I put a chlorine here, rest assured this molecule, chloromethane, is polar, okay, is polar. Even if I replace another one here, even if I replace another one here, it's going to be still polar. And if I replace one more here, this molecule is still going to be polar, because I said at least one is different, right? And what happens is, if I replace all of them with chlorine, now all the peripheral atoms are the same. This tetrachloromethane ends up being non-polar. Okay, it ends up being non-polar, because again the same thing, all peripheral atoms are the same, the bond angles are all the same again, so they will all cancel each other out. All right, so you draw the molecule, it has one lone pair, is most likely polar. The peripheral atoms are not the same, it's polar. Okay, so this is what bond polarity is all about. So in this part here, you can see polar molecules. It explains to you exactly what I just told you just now. Okay, so like in this case, you see these molecules are all polar. Look at in this case here, BF. So what happens in this case is you see these angles are all 120. This angle is 120. This angle is 120. Here every angle here is 109.5. Okay, and in this case, although all angles are also 109.5, but the peripheral atom is different. Okay, the peripheral atom is different. So these molecules are said to be polar. So all molecules which the polarities don't cancel out are called polar molecules, right? So then this will help us to get into the next part, which is called secondary bonding.